either find the derivative for one-dimensional function, or you can solve problems for multi-dimensional functions. And again, let's consider it should be noted that k here should be integers, it should not be fractional order derivatives. So let's go back to this function first. How can we find the first order derivative from the function? To solve the problem, what we need to do is first to generate a sample data set for x and y as we did before. Generate the x vector and find the values of y. And from this data, we can easily obtain a cubic spline interpolation or B-spline interpolations to the same problems. And based on the splines, we can find the numerical derivatives for the original function. Since the original function is known, we can easily find the theoretical form of its derivative, and then we can compare the results. So these are the code that we want to execute. First, specify the original function in a symbolic way, and then we can easily draw the first order derivative of it. And then we can generate a set of data. From the data we can generate a cubic function, a cubic spline object. And then we can perform first order derivative to it, and then we can draw the results in slash lines. And also we can create a B-spline object, and we can also find the first order derivative to it, and then we can display the results. We can display three results in the same graph, and then we can compare them. There is a problem there. Well, there are some tight links in the PVT files. Once you have had this problem, then I would suggest, if you are familiar with latex, it is okay. If you are familiar with it, you can install latex, and also another tool called text point. If you install these two packages, you will have a text point label here. And then you can double-click the graph and get the source code. If you do not have that, this is simply a figure object. So once you have installed the latex and text point, what you can do is double-click it and find the code itself. Otherwise, you cannot do. You cannot do things like this, because it is just an image file. And for most of the links, it should be okay in the PPT file, but for some particular ones, they may not be good enough. So this is the interpolation result. The function is slightly different from the one we used earlier. Here, the solid line is for the theoretical results, and these two are respectively to cubic splines and B-splines. Normally, we can expect a better fitting with the use of B-splines. So now let's consider high-order derivatives. Let's consider second-order derivatives from the x-spline. So even higher order, fourth order derivative from the cubic spline. EST1. If we display it, it should be something like this. you are performing a second order derivative, you will have something like this. P1. And we can display the coefficient of it. It's P1 dot COEFS. You will see that the coefficients are no longer third-degree polynomials. It is only a linear form. So why this happens? It can be easily interpreted like this. This is the original cubic spline result. If you take first order derivative, then this one will be obtained by 3 times 0.9139 times x minus 0.36 squared. So if you take first order derivative to the cubic function, you will have a second order function. If you take a second order derivative to it, what you left is the linear form. And if you take third order derivative, what you obtain is the constant. So you cannot take higher order derivatives to the cubic spline functions. However, for B-spline functions, you can take higher order derivatives. Normally, you cannot get the derivative higher than the original order of the B-spline. For instance, this one is created by the fifth order B-spline. You cannot take higher order derivative higher than 5. If you take that derivative, you may not get good results. However, for first order derivatives, this one works very well. And again, here we can